putting it all together. So what did we learn so far? We learned, first, we can use the remainder theorem to see if a number is going to be a factor. We're going to use this if the first factor is not given to us. So we need to look for a factor to begin with. Then we learned that with the factor theorem, given a factor, so when we find our first factor, we can use long division or synthetic division and confirm that the remainder is 0. And then we can use the rest of the steps, writing the divisor times the quadratic quotient and then factoring the quadratic quotient to fully factor the given polynomial and then finding the zeros that way. So we're going to use those two theorems together in order to understand what we're doing. And also we know that if we have a polynomial of degree n, then we would expect n factors, n linear factors, and as a result, we're gonna expect n zeros of the polynomial. And these are complex and not necessarily imaginary. So let's put that together. Factor the polynomial functions into linear factors, then graph the polynomial. So in this case, I do not have a polynomial. I do not have a factor to begin with, so I will need to test for a factor. I'm going to set x equal to 0, and then negative and positive 1, and then positive and negative 2, and etc. in order to find. Now we're going to use the remainder theorem to find a factor. So I will take each of these numbers and I'm going to plug it into the function and see which one will give me 0. The one that is going to give me a 0 is considered a 0 of the polynomial, and it's going to make x minus that number equals to a factor. So I'm going to try the 0. F of 0 equals to 0 cubed plus 2 times 0 squared minus 4 times 0 minus 8. That is equal to negative 8. So is not a factor. So 0 is not a factor. Or let's say x minus 0 is not a factor. I'm going to try 1. F of 1 equals to 1 cubed plus 2 times 1 squared minus 4 times 1 minus 8. That will give you negative 9, sorry. That 1 is not a 0. Or x minus 1 is not a factor. Let me scratch that. X minus 1 is not a factor. The previous one is x minus 0, which will give you x. In other words, 0 is not a 0, 1 is not a 0, and etc. I tried f of negative 1 already, and for the sake of saving some time, I'm going to jump to f of 2. So 2 cubed plus 2 times 2 squared minus 4 times 2 minus 8 will be 0, which means x minus 2 is a factor. So we're going to proceed with the factor theorem. So this is basically the remainder theorem, and now we're going to proceed to the factor theorem. So we're going to apply the synthetic division, x cubed, x squared, x and c. So I'm setting up here, and the number we found, which is 2, we're going to divide by that number, and then we're going to set up the coefficients. The coefficient of x cubed is 1, coefficient of x squared is 2, coefficient of x is negative 4, and the constant is negative 8. Now we're going to do the division. The first number comes down. 1 times 2 is 2. We're going to add 4. 4 times 2 is 8. 8 minus 4, or negative 4 plus 8 is 4. 4 times 2 is 8. 8 negative 8 plus 8 is 0. So we verified here that actually 2 is going to be a 0, and it's going to be x minus 2 is going to be a factor. Now we're going to go to the next step, which is rewriting the polynomial. So f of x equals to the divisor, x minus 2 times the quotient. So we're going to scratch the first one, and then we're going to connect like that. So the quotient is x squared plus 4x plus 4. Now we will factor the quadratic. So we will have x and x. We need two numbers. Their product is 4. Their sum is 4. That is positive 2 and positive 2. So in this case, we have 3 zeros of the polynomial. We have 3 zeros of the polynomial. If we set the first factor equals to 0, we will get x equals 2, and the multiplicity here is 1. And then notice how those two are the same, so we can basically rewrite this expression as x minus 2 times x plus 2 all squared, which means if we make the second factor equals to 0, x plus 2 equals to 0, that will lead to x equals negative 2, and the multiplicity here is 2. So the multiplicity of the second factor for the second 0 is 2. So we have this 0 and we have that 0. Okay. Now we're going to graph it. So I'm going to put the zeros with their multiplicities. So I will put the zeros with their multiplicities. The first 0 is at 2 and the multiplicity is 1. I'm just going to write 1 here just to remind myself. And then at negative 2, the multiplicity is 2. So the multiplicity is 2 here. Now let's look at the end behavior. In this case, we have a degree that is odd, which means the behavior is going to be either this way or that way. So which one is it? Notice how the leading coefficient here is positive 1, which means the graph is increasing. So the trend is going to look like this one. So I know that eventually the line here is going to go this direction and the line here is going to go this direction. And then something is going to happen in the middle. I can also find the y-intercept, which is basically I already found by plugging x is equal to 0. So the y-intercept is 0 and negative 8. I'm going to mark it here. So that is the y-intercept here. So now I can basically sketch my graph. I know that at x equals negative 2, the multiplicity is 2, which means the graph is going to touch and bounce. So touch and bounce. Now it's going to go through the y-intercept, and then the other 0 is linear, which means the graph is going to just go across the x-axis straight in a manner similar to the linear functions. So that is basically a sketch of the graph, and that is how you're going to put what you learned together. Now it is your turn to try the second example. The same way I did this problem, you're going to first find the factor or the 0, which is, in my case, it was 2. Use that in order to verify with the synthetic division that you actually have a factor, and then using the synthetic division, write the polynomial as a multiplication of the quotient times the divisor. Factor the quotient because it's going to be quadratic. It's going to be easy to factor. If it's of a higher degree, then you're going to repeat the process again by finding another 0 in order to factor the third degree polynomial that remains here. And then using you're going to set each factor equals to 0. You're going to find these zeros with their multiplicities, and then you're going to use the information we learned before about the end behavior of the polynomials in order to graph the polynomial. Don't forget to determine the y-intercept. The process is easy. You're just going to plug x is equal to 0 and solve for y. So you get the y-intercept, and then you can sketch your graph based on what you have learned so far and what we have learned in this section as well. Hopefully that is clear. One last thing here, using the linear factorization theorem to find polynomials with given zeros. So a vital implication of the fundamental theorem of algebra is that a polynomial function of degree n will have n zeros. So that's basically what we're repeating, what we're saying here. In the set of complex numbers, we have n zeros in the set of complex numbers because we determined that every real number is going to be a complex number, but not vice versa. If we allow for multiplicities, of course. This means that we can factor the polynomial function into n factors. So that is basically what we have gone through so far. The linear factorization theorem tells us that a polynomial function will have the same number of factors as its degree, the same factor as its degree, and that each factor will be in the form of x minus c, where c is a complex number, because we know that real numbers are complex numbers. Let f be a polynomial function with real coefficients. Suppose that a plus bi, such that b is not equal to 0, is one of the zeros of the polynomial f of x. Then according to this theorem, using the factor theorem, we know that the conjugate, we know that by the factor theorem, we know that x minus that complex number b plus bi, where b is not 0, is a factor of f of x. For f to have real coefficients, then the conjugate of that number must be a factor as well. The conjugate, which basically x minus a minus bi, and b is not equal to 0, has to be another factor. So when you have a complex number as a 0, the conjugate of that complex number has to be a 0 as well. And that leads us to the complex conjugate theorem. According to the linear factorization theorem, a polynomial function will have the same number of factors as its degree, and each factor will be in the form x minus c, where c is a complex number. If the polynomial function f has real coefficients and complex zeros in the form of a plus bi, meaning the complex zero has to have the imaginary part, then the complex conjugate is also a 0. So the conjugate is when you change the sign of the imaginary part of the complex number. That is a minus bi. So that is basically what this theorem says. So if you have a polynomial that has 2 plus 3i a factor, then or a 0, then 2 minus 3i must be another 0 as well. So that is what this theorem is basically saying. And that basically concludes section 5.5. If you have any questions, please let me know.